Here's another thermodynamic process called an isovolumetric process or an isochoric process. It's known by either one. And in this case, what happens is the volume remains constant during the entire event. And so what happens on a PV diagram, a constant volume would mean a vertical line like this, hence no area. So no work is done on or by the gas during a process like this. All we're doing is thermally exchanging heat in or out. So it'd either be like having a candle flame underneath the piston cylinder and not letting the piston move, or putting it in an ice bath and letting heat exchange out of the cylinder and not letting the piston move up or down. All right. So a problem like that might be something like this. A monatomic ideal gas has an initial temperature of 300 degrees Kelvin, constant volume, remains constant through the whole problem. You've got 3 moles of gas. So how much thermal energy must be added in order to raise the temperature to 380 degrees Kelvin and calculate the change in the pressure of the gas? So these are our equations that might be relevant for this problem. Start by writing down our knowns and unknowns. So here's our initial temperature, here's our final temperature, here's our volume, which remains constant. We've got 5 moles of the ideal monatomic gas. They want to know how much heat must be added. So we know that the work done is going to be 0, simplifying our equation, and we know that delta U is equal to 3/2 nR delta T. Number of moles times the gas constant times change in temperature. So putting in what we know and solving algebraically, we would get that we would have to add, because Q is positive, so we would have to add 4,990 joules of energy in order to get that temperature change in that cylinder. Second thing they wanted to know about is what would the change in the pressure, delta P, of the gas be, since we're holding the volume constant. You know, if you're increasing the temperature, that we're going to have to increase the pressure. It's like a pressure cooker. So in this case, we can use a form of PV equals nR delta T, and in this case we're changing the pressure here, holding the volume constant, so solving it this way will work because we're not varying the volume. And solving for the change in pressure, we would just substitute in our 5 moles, 8.31, 380 minus 300 for our temperature change again, divided by the volume. Make sure you're in SI units, cubic meters, and we'd get a change in pressure of 2.22 times 10 to the 6 pascals.